Okay, so I started off by, when I was writing this talk, by I wanted to give a talk about how sort of principles and laws and axioms could help us do asynchronous programming more easily and more safely and sort of reason about code more directly. And I think that's a really interesting topic. But as I was writing the talk, it just sort of like evolved into something else, which I think is a lot more interesting. So we're sticking with the title, but the title doesn't necessarily relate completely to the material. And what I wanted to, what this talk evolved into instead is actually a really deep dive into how the current version of scalaz-stream works. Because there's a lot of clever ideas in there. And we are, for those of you who don't know, we are redesigning scalaz-stream. Like there's a brand new algebra, there's a lot of changes that we're making to it. And there's really good reasons why we're making those changes. But I think there's some lessons that we've learned along the way with the existing algebra and those and the existing implementation. And those lessons can be applied to other things as well. So we're going to look at what we have now and sort of what's cool about it. And what's not cool, and we'll go from there. I don't think, at least not yesterday, I don't think the Gitter stuff is working really at all, so please feel free to ask questions at any point during the talk. It will be substantially more interesting if you do so. I'm going to start with a quote, which is probably not actually a quote, but asynchronous programming is hard. Very, very hard. It's hard to get it right. It's very easy to get it wrong, and when you get it wrong, it's very hard to figure out how you got it wrong. Very strange things will happen in very strange ways, and no one really understands it. Victor Klang is also great, because you can put any words in his mouth that you want, and he's not here anymore, so you can't really object to it. So what do I mean by asynchronous programming? Because I want to be somewhat precise about these terms here. Asynchronous programming is not concurrency. Okay, it's not multi-threading, it's anything like that. In fact, asynchronous programming is sort of the opposite of multi-threading. It's never sitting on a thread. I define asynchronous programming to be never blocking, never waiting for anything in sort of any sort of fixed way. It's really all about callbacks. You register a callback, and this is what we often talk about with an asynchronous await, is someone outside of us is going to push data in that's going to tell us that we need to wake up and perform some work. You should think of Node.js as basically the crudest possible incarnation of this concept. I don't have a formal proof that there is nothing more primitive than Node.js, but it's probably pretty close to true. There's a lot of, Node.js is very, very asynchronous. It's not concurrent, because it's all on a single thread, but the abstractions are very, 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 very low level. We can do a lot better than that in some ways, and scalaz-stream is one of the attempts to do this. So that's asynchronous programming. What about laws? What do I mean when I talk about a law? Because even though we're going to talk mostly about scalaz-stream, it's still important to kind of keep this in mind. Well, laws certainly have nothing to do with any sort of legal system or moral reference or anything like that. What they actually are dealing with sort of mathematical truths that we remain consistent with. So here's an example, right? We know that the expression on the left is equivalent to the expression on the right. And we know this because we have a couple of laws that deal with algebra, both in the numerical sense and in the abstract sense, that tell us, for example, that addition is associative. Between associativity and commutativity of addition, we can derive the left-hand side of the former expression from the right-hand side. And this is a law that we can keep in mind. This allows us to make rearrangements and simplify expressions in math. Because programming is math, we are allowed to do the same sort of thing with code. So here's an example which might be a little bit more familiar. The expression at the top is equivalent to the expression at the bottom. And I can tell you that without knowing anything about the implementation of log or the implementation of make shiny or any of the other functions that are on the screen that I can't remember the name of because I wrote the slides very late. And I know that these are equivalent, because they are defined to be equivalent because we have a law which says they are equivalent. And this has nothing to do with the implementation of for comprehensions either, right? It's not a desugaring thing, it's a law. And the law is this one. It's the associativity of monads. The thing on the left corresponds to the bottom part of the screen. The expression on the right corresponds to the top part of the screen. And I know that these two are equivalent. I can move back and forth between them freely. Anything that purports to be a monad is also claiming to obey this law. And because it claims to obey this law, I can make this rearrangement. So laws, in a sense, can be thought of as refactoring, but with your mind, right? You're allowed to make these changes to your code and sort of cut and slice things up and move things around. And as long as you are adjusting things and rearranging terms in accordance with the laws, and the terms that you're playing with are in fact obeying the laws that they claim to obey, then everything will be safe. Laws allow you to forget things about your code. More importantly, they allow you to forget things about other people's code, where other people may be defined as a past self. You don't have to remember sort of the implementation details of the initialize function, right, from the previous slide. All you have to remember is that it obeys certain laws. They simplify reasoning because you're throwing information away. It is actually an entire coincidence, by the way, that Runar's keynote from yesterday has tremendously overlapping themes with my keynote from today. We didn't coordinate on that, but there's going to be a lot of recurring themes here, and it's basically that you want to simplify things down. You want to have smaller, sort of more focused and narrowly tailored abstractions, very principled abstractions that allow you to throw away things and reason more. So things that you can throw away, for example, as they relate to asynchrony, would be things like finalizers and handling. And by throwing them away, I don't mean you don't have them. I mean you don't worry about them. They work. You can have laws that say, well, if this executes, then this runs when it's done executing, by definition. And you suddenly no longer have to worry about life cycles at all, because you have this law which says, well, this always works, regardless of how you've composed it, regardless of how this piece is connected to that other piece. Two components behaving differently together. I swear this is the root of all evil in software, is like, I have thing A over here and thing B over here, and these two parts of my program do one thing when I run them in isolation, and if I put them together, they do something completely different. That is the root of all evil in software, honestly, right there. And when you have very lawful, very principled programming, frameworks, this problem goes away. You don't have to worry about it at all. It's done. It's gone. And that is hilariously powerful when you're dealing with more and more complex things like asynchronous programming. And of course, we all like reformatting code, pruning things, moving them around, sort of making the code look prettier to our eyes. And the truth of the matter is that you are completely allowed to do this, and you are justified in doing it if you're working within sort of the framework of the laws, which, as I said, often allow you just to make rearrangements. And these sort of adjustments, as long as you're working within the framework of the laws of the underlying system, you know that they're safe. You don't have to think about, oh, well, if I do this thing before that thing, then the widgety thing happens at the wrong time. No, it all works. So this is laws. This is principled software, and this is what we strive for with scalaz-stream with respect to asynchrony. So what specifically is scalaz-stream? This is not an intro to scalaz-stream talk, but I'll do an intro to scalaz-stream slide. It's a framework for modeling asynchronous programming as codata. If you don't know what codata is, Paul Phillips had an excellent talk yesterday in which he explained all co-words everywhere. I'm sure codata was in there somewhere. So we won't talk about that at all. Asynchrony as codata, and this turns out to be a very, very natural pairing. This is one of the ways in which we can use these functional abstractions to be really powerful and kind of make things a lot simpler than they would have been if you just sort of had bare callbacks floating in the ether of JavaScript. Ecosystem of useful tools and combinators. So this is I'm happy to say, a very growing ecosystem of tools and combinators. Some of them are in the scalaz-stream framework. Some of them are outside of it. There's a lot of frameworks that build on top of scalaz-stream that do extremely nice things. Things like allow you to write servers, which is sort of a good thing. And other such things like that. It has support for concurrency. Now remember, I drew a distinction between concurrency and asynchrony at the beginning of the talk. Concurrency is running two things or multiple things in parallel. Asynchrony is not really blocking while you're running things. And they are they're related concepts, but they're not, in fact, the same thing. Scalaz-stream allows you to do both, which is very, very important for practical use. It has a clean library of transducers, which is, of course, a term which is very overloaded by everyone, up to and including the Clojure community, and I feel justified in overloading it more. We also have a support for NIO, which is a really, really natural fit for any framework that does asynchrony. In fact, I think this is one of the primary reasons why you would care about asynchronous programming is async IO, because now you're talking about being able to elegantly handle resources on networks and files and things like that without sitting on threads waiting for stuff that may or may not get back to you in a timely manner. So it's much, much, much more efficient. Much, much, much more efficient. So that is as much intro to scalaz-stream as I'm going to do. It's time to dive into the really nitty-gritty details. And even if you're not super familiar with the scalaz-stream framework, I hope this will still be interesting to you, because code is cool regardless of what it does. So deep, dark, and oh my gosh, that's completely impossible. It's a picture of Mordor. You can't see that at all. I am terribly sorry. Process. This is the root of the scalaz-stream algebra. All right. So we have a process type, and it takes two type parameters. One of them is an effect. The other one are the elements that a process emits. So an element can emit one or more, or zero or more, actually, elements, one after the other, in this very ordered way, and it can perform zero or more effects. So it's this kind of two things that a process could potentially do, and then everything else is plumbing around that. So the effect is parameterized on the left, the elements are parameterized on the right, and we have the requisite pluses and minuses in order to make the code compile. Halt and emit. These are the two simplest cases of the algebra. A process can be empty. So the halt process does nothing other than immediately stop, and it halts with a cause. I'm not showing you what cause is, but you can use your imagination. Basically, you could either end with sort of a normal, I made it to the end of the world and now I'm done, just sort of nothing unusual about that. Or you could end with something terrible exploded and now I'm out of memory and somehow I caught that and gave it back to you. So there could be an exception inside of here, or there could be some sort of normal signal of some sort. Anything like that might be inside of a cause. And you see that a halt doesn't emit any elements and doesn't perform any effects. So halt is a process of nothing, nothing. Emit is where you get data from. This is where you get elements. It's how you produce things, and you emit a chunk of elements represented by a seek, because efficiency. It doesn't perform any effects. So again, the first parameter is going to be instantiated as nothing. So it's a process of nothing and a. That is an emit. So in terms of translation, this basically looks like this, right? So we might construct a process that contains the elements 1, 2, 3, 4 in that order. And if you look at what this is represented as under the surface in the algebra, it's going to be emit of vector 1, 2, 3, 4. Very, very complex. We could have the empty process. And the empty process under the surface is going to be represented as a halt with the signal end. So this is just the normal, I made it to the end of the stream and nothing exciting happened, so I'm boring and please be done. That's what halt of end means. Obviously, these pair of things in and of themselves, these pair of cases aren't very useful, but in combination with other things, maybe they will be. So append. This is what allows us to, remember I talked about the number one problem in software, right? Component over here and component over here, and they do one thing in isolation, but put together they do other things. Well, append is how you put them together. So we have the component over here, which is represented by head. I didn't name this. I don't know why it's called head. I would call it front, but that's just me. So the first part of the thing, the left-hand side of the double plus, is the head process FA, and the right-hand side, very confusingly, is this stack. It's a vector of function from cause to process FA. Very weird signatures right here. And this is where we start to get into extreme bizarro land. There is a good reason for this, and we're going to explore this in a second. I'm not going to show an example of like a multi-element vector inside of an append, but basically what you should think of is this allows us to do like A append B, append C, append D, and turn it all into a single append node. right? Because A will be the head of the append node, and then B, C, and D will all be in the same vector stack. So it gives us a sort of very constant or pseudo-constant time append, regardless of how deep we're going in the stack. But that doesn't, of course, explain the sort of function cause to process thing, but we're going to look at that in now. So process 1, 2 plus process 3, 4. This is going to, so we've got 2 emits here, right? We're going to emit on the left-hand side, emit on the right-hand side, and we have to append them together. So it looks exactly like you would expect. We have an append node that has an emit on the left-hand side, and then on the right-hand side, or rather inside of the stack, we have this complicated function thing. Because remember, we have to look at the cause. We get the cause, and then we use that to compute the next part of the process. And we look for end. Remember, this is the boring, I made it to the end of the world, now I'm done signal. And if we get the boring, made it to the end of the world signal, then we emit vector 3, 4. However, if we don't get the boring end of the world, I'm done signal, let's say maybe we got an error somewhere and we want to shut down the stream, well, we want to kind of skip out of this append if we're trying to shut down the stream. We don't want to move forward, so we're just going to halt. So this is why it's actually useful to have these cause functions inside of append, is it allows us to shut things down prematurely like this. It also allows us to unify appends and finalizers. So finalizers are represented with this onComplete function, and what this syntax means is run the server process, or rather when the server process is run, when it completes, for any reason, I want you to run the shutdown app function. So this sort of corresponds to the finally clause in a try finally, if you think about that. And this right here is life cycle stuff, right? This is where asynchronous programming starts to become really hard and challenging. OnComplete makes this element of it really easy. And because of the way that the append algebra works, it's actually very straightforward to represent. So we have this append node. On the left-hand side is the server. This is just like it was when we did the ++. And on the right-hand side is shutdown app. But you notice we're no longer looking for end. We just say, whatever cause, for whatever reason you stopped, I want you to run the shutdown app process. So this is really, really cool. It's really cool in several ways, and one of the reasons this is cool is it means that if someone gives you a process and you're trying to like traverse the algebra of this process and find all of the data that's inside of this process, right, which might actually be a very useful thing to do that a lot of us do all the time, you can't be absolutely certain that you have found all of the data unless you have traversed all of the appends, right? Because someone may append more data to the process, but some of those appends are going to correspond to finalizers. So in other words, we have constructed this algebra in such a way that finalizers are guaranteed to run. No matter how you implement your process evaluation, no matter how you decide to traverse the process, you're guaranteed to hit a finalizer if that finalizer is in the stream. And this is really powerful, right? This is sort of hits on a really important principle of algebraic design, which is that you want to think about what sort of invariants you want to enforce, right? The invariant in this case being I want to ensure that finalizers run at the appropriate time. And you want to think about how can you force, like actually outright force adversarially people to make sure that they happen at the right time. And this is what this algebra achieves. So there's sort of a method behind the madness of the crazy vector cause to process thing. And this is the method behind the madness. It forces people to do the right thing. Where by people I mean me. Final node. We have one more node in the algebra, one more thing that does things, because you'll notice that the notable feature of process that we haven't enabled yet is the ability to perform effects. The ability to add effects into the stream and actually run them and do things that talk to the outside world, which is presumably what we all want to do every day. And the node at which does this is await. So here's where we get to the really, really exciting and clever stuff, right? So the await node takes 3 type parameters, not 2, which is very confusing. It takes the effect type, it takes the element type, which is A, not E, and it takes some other existential type, E. This E type, you'll notice we don't pass this along to our supertype process. E is just completely local to our specific await node. And there may be many await nodes in a stream, all of which having different E's. It's all completely existential. That E is produced by the effect. So rec is an effect that produces an E, and then we have a function that consumes the E and gives us a process FA. Now this is really, really, really cool for a number of reasons. Number one, it allows us to have effects of arbitrary type inside the stream, right? So our stream can be reproducing one thing, and we can have effects that produce completely different things, and that's okay. In fact, we can have effects that are producing things that are all over the map, not even consistent with each other. And that's completely okay, as long as for each of those existential types that the effects produce, we can provide a function which converts it to a process FA. So that's really, really, really nice. The other thing that this gives us is this is basically an encoding of the free monad. And I'll talk about that more in a second, but it gives us some really, really powerful things. The third parameter here, preemption, this is new in scalaz-stream 0.8. So if you're familiar with 0.7, this will look a little bit weird. We're not going to talk too much about this, but this is basically important for handling concurrent interrupts and making sure that resources are safely released. We used to try to do this kind of like magically detecting finalizers and sort of wandering through the stream and the ether and making sure everything worked. And it turns out that we couldn't do that. So we're not doing that anymore. All right, so how does this actually look like in terms of surface syntax? Well, let's say we have an effect, server starter, that probably starts a server. And it's of type task of server. So it starts the server and gives it back to us as a value. We want to put that into a stream. So we're going to use this eval function on process, which gives us a process of a single element that performs the effect and gives us the value of the effect and just emits it in the stream. And in terms of the algebra, this looks basically exactly how you would expect. We have an await node. We are awaiting the results of the server starter effect. And then the first function, which you remember is the receive, that's going to take the server and wrap it up inside of an emit of vector. By the way, you'll start to notice the wonderful efficiency of this library in that we have an emit of vector, and that vector contains a single element. Single element vectors, yay! We have those all over the place, and it's a large reason why our memory footprint is insane. The third parameter here, like I said, we're not talking about. It's the preemption handler. Really what we should do in here is we should have some other effect that shuts down the server in the case that we were interrupted for some sort of crazy reason. We're not doing that because YOLO, this is probably wouldn't fit on a slide. So this is the await node. Now I said the await node is basically an encoding of the free monad. It's in fact an encoding of the bind case of the free monad. And that gives us a lot of power. It gives us a tremendous amount of power. Among many other things, it allows process to have a flat map function regardless of what effect type is inside of it. So the F inside of process doesn't need to be a monad. So in other words, it doesn't need to have a flat map function. It doesn't even necessarily need to have a map function. We could define flat map regardless because we're defining flat map through the await. Right? The await is how we get flat map. And this is really, really, really powerful. I would encourage you, especially if you're sort of studying free monads and trying to understand kind of how they work, looking at await is really interesting because it's a very different encoding of free than what you would normally see. Await is also sort of multiple things all in one. It is the only introduction rule for effects. So it's the only way you can perform an effect in a process is to have an await node, while emit is the only introduction rule for values. And this tangling of concerns, the fact that we're both the encoding of the free monad and the only way to get effects, is actually a very serious problem, right? It sort of seems clever, like it does this cool existential type thing and it sort of hides things from the outside world and it kind of encodes stuff in this really neat way. Like the await node is really, really sort of aesthetically pleasing once you kind of wrap your head around it, but it turns out to be the root of almost all of our problems with the current algebra. So that's the bad news. We're going to look at the good news first, though, so the white-collar part of the white-collar crime. And the good news is that we basically have a lot of properties which are really nice. One of which is very important, is referential transparency. Referential transparency, in a nutshell, says if it works, it always works. I don't know why this is a controversial property to have. It seems very, very natural to me. Like you would want this, right? You would want it. There are no magically broken anything. Things just, if it works once, it will work always. And that's really, really nice. You can put things in any order. So if I have a process A and a process B, and I do A append B, that will do the things in A and give me the results, and then it will do the things in B and give me the results. And if I do B, then A, it will do the things in B and give me the results, then do the things in A and give me the results. Basically exactly what you would expect. Again, this is, like, I sort of stress this because there's a lot of ways you can not have this property, and it makes building software much, much, much harder. Scala-stream really, really encourages it, and our algebra is pure, and it controls the effects. Right? The effects are sort of contained within the await node, and they're referenced within the type, and so it's very easy to reason about what your processes do. And it turns out that as you're building larger and larger and more complex pieces of software, this benefit sort of hits you in the face harder and harder and harder every day about how great it is and how really, really nice it is to work in this model. Absolutely no fear. Refactoring code is sort of fiddling with things or adding things to a code base. I have a really complex, sort of gnarly code base at work written in terms of scalaz-stream that actually implements a peer-to-peer server and sort of connections coming up and down and coordination and multiplexing data back and forth. And I don't even, like, even the gnarliest bits of the code, I'm not really afraid to go in and mess with things because I know that all of these properties hold. Referential transparency is really, really nice for this. You get real actual composability. Referential transparency is the root of composability, and composability is the root of sanity. So that's enough of sort of abstract things. What do we get practically, right? File manipulation. File manipulation is really, really easy. I know file manipulation of the sort that's trivial and you can put on a slide is not interesting, but use your imagination and pretend I'm doing something more exciting than emitting words. We open a file using the IO lines R combinator. This is something that's built into scalaz-stream. And so we're reading all of the lines in the file foo.txt, and we're splitting them based on white space, and then we spit those all back out to standard output lines. And you notice what is not in this code is any mention of closing the file, or any mention of handling errors halfway through the stream and making sure that the resources get shut down. Again, this stuff seems really trivial when you're talking about one file. It seems a lot less trivial when you're talking about 100,000 files. It turns out that all of the logic for making sure these resources get cleaned up is contained within the lines R combinator. So the lines R stream gives us this stream of strings coming up out of this foo.txt file, and it does it in a way which is incremental and safe. And also, it turns out completely asynchronous because it's not actually waiting for like file handles or things like that. It just sort of DMAs it to us. It's very, very, very nice in that respect. The other thing about it is, remember, we have these properties of composability, right? If process A does a thing and process B does a thing, then you can put them together and do both the things. Well, in this case, maybe we might want to do both the things concurrently. So let's say we have two files that we want to read, foo.txt and bar.txt, and let's say that either they're on two different platters or we're on an SSD or something where reading them concurrently would actually make sense. And we can do them simultaneously. Again, we're using the lines R combinator on each file. And again, we're not making any mention of when there's an error like the foo.txt file didn't exist, shut down the bar.txt file even though we've read half of it. Like we don't worry about any of that sort of coordination stuff. All we do is we use these safe combinators to create a process that uses the algebra that we've been looking at under the surface, and we use this merge function to put them together. So this is kind of our first look at concurrency in scalaz-stream, and it turns out that concurrency is comparatively easy to implement on top of this framework that gives us very powerful and very safe asynchronous abstractions. So just because it's fun to see how the sausage is made, how does concurrency work inside of scalaz-stream, right? Because we haven't really talked about carrying around thread contexts or anything like that inside of scalaz-stream. All we really have are effects and appends and such like that. And it turns out that it works by having a function like this. So this function is not pure or referentially transparent in any sense of the word that is sane. It's the step async function. And what this will do, it's a function on process. It's hidden because it's very, very unsafe to use. And what it will do is it will run a process. It will sort of try to walk through the process algebra of the underlying stream until it gets to an emit or until it gets to the end of the stream. And critically, it will do it on another thread. So there's actually, I hid the parameter, but there's an executor that comes into here and gives us a way of scheduling the task concurrently. And when it hits this chunk or it hits the end of the stream, that's what the sort of left, right, bar, or thing, scalaz thing is. When it hits one of those two, it will invoke the callback that we have given it. That's the function CB, the parameter that we give there. Meanwhile, the step async function has returned to us a function from early cause to unit. Now, early cause is basically cause. And what this means is we have a way of interrupting the process which is now sort of concurrently running on this other thread. We have a way of shutting it down. If, for example, we were running two of them and one of them like hit an exception or something like that. This function, the implementation of this function, by the way, is mad, crazy insanity. If you think your concurrent code and like write barriers are hard, it's amazingly insane. I never want to see that code again. Anyway, the way it works, the way you would use it is about as straightforward as you would expect. Not really. So we have two processes, lines 1 and lines 2 from the previous example, right? And we want to run them both in parallel. We would do it with this step async function. And this step async function, we're going to call it on both of them. It's going to return to us right away. We're going to get interrupt functions as a result. And we're going to register callbacks. We're going to give callbacks to these step async functions. And when we get, if we get an error from one of them, then we'll interrupt the other one. That's what's happening kind of in the left case there. And in the right case, we've got a chunk, which is lines. And we would presumably put that chunk on a queue or process it, apply some function. I don't know. We would do something with it that would be interesting and not completely trivial. This is very gnarly and complex. This code is deep inside of scalaz-stream in one place or another. The thing that's cool about it is that because of how we constructed the algebra, despite all of the side effects that are going on here, like all of the weird sort of very much not referentially transparent stuff, it's still actually safe. There's things about this that are very safe. The effects are still very controlled because they have to be evaluated in completion. The finalizers are still guaranteed to run, right? If we're step asyncing a process, we're still going to step through the finalizers. We have to in order to either hit the end of the process or get all of the chunks of data. So this is kind of cool. It's kind of an interesting bit where we did something really gnarly and terrible under the surface, but because of how we constructed our algebra, by definition, we had the safety properties that we wanted. We had the laws that we wanted. I've mentioned finalizers. Here's a somewhat more complex example than we had earlier. This is actually basically how the lines are combinator is implemented. And what we have here is we're rather than using eval, we're using the await function on process, which constructs an await node a little bit more directly. And we're awaiting the server.start effect. And that, again, as before, is going to return to us a server. And what we're going to do is we're going to emit that server. We're going to produce it to the world. And when we're done emitting it, we're going to finalize the process by shutting down the server. Now, when you actually first look at this actually looks like, oh, well, that's probably going to be really premature because we're going to give the server to someone else. And then before they can do anything with it, we're going to shut stuff down. But it turns out that this interacts really, really nicely with the flat map function that we got for free, pun intended, out of the await node. So when we flat map on this service process, which by the way could be defined in a completely different file or library or combinator or something that we don't understand, we flat map on this service process, we get the server out of it, and the finalizer hasn't run at the point where we get the server out of it. So we can use this server safely, and then service will sort of magically run that finalizer and shut us down without us really having to worry about it, right? So this is a really nice property that comes out of, again, the way that we constructed the algebra. Really, really nice. Transducers. Like I said, transducers are really not a very well-defined term by anyone, much less Clojure. We're not going to define them very well either, but I take them to mean, in the context of scalaz-stream, is a state machine that modifies a stream based on the input values, right? So we're all familiar with encoding state machines. We all do it all the time. The transducers in scalaz-stream allow us to do it very elegantly based on input. One element after another sort of transitions us through the state machine. It's an extremely common pattern. I do this all the time, and there's a ton of really common combinators which it turns out are actually implemented in terms of this transducer mechanism. Things like take, right? Take is a state machine. You start out in one state where you're accepting more input, and you decrement down your counter until you hit 0, at which point you're no longer in that state and you're rejecting input. Scan. This is a less familiar function, but it's basically fold, except it emits elements along the way. Parse. You can actually implement parsers on top of scalaz-stream that run incrementally with all of the properties that you would want, and they're implemented on top of this state machine transducer mechanism. The cool thing is, because of how our algebra works, especially because of how the await node works, you can implement transducers that are themselves a stream. So transducers on a stream are themselves a stream. It's really neat and quite nifty the way that it falls together. So here's kind of how the Surface API works. This is the implementation of take, and this is actually what it looks like in the library. We have a take of A that's going to give us a process 1 from A to A. That's a process 1, a transducer that transforms a process that emits A and gives us a process that emits A. That's the output of the transduction. And we have a parameter n. If n is greater than 0, then we're going to asynchronously receive one element of type A. If we get that element, we're going to emit it and then append take n minus 1, exactly as you would expect. If we're below 0 or below, then we're just going to be done. We're empty. We finish off. And we're not going to take any more elements from the left-hand side. Here's a more complex example that we're not going to dwell too much on. But this is basically, I'm following through on my threat to implement a parser on top of transducers. This is parentheses matching, right? This is the #1 use case worldwide of people trying to match parentheses all the time. I do this. I don't know. It's very useful. But this will match parentheses and make sure that they're balanced. And if it can prove that they're not balanced, it will emit a false. And if it proves that they are balanced, it will emit a true. Everybody start your photocopiers. This is what's cool is that you can do this. I guess it's not really all that useful, but it's cool. It's very cool. So how does this work? Right? How is this actually implemented? Because I promise you, this is implemented on top of the existing scalaz-stream algebra. There's nothing new or magical here. There's nothing sort of special that we're doing or hooks that we're using. It's all implemented on top of the same thing. And it turns out that process 1 is, in fact, a process. Process 1 takes 2 type parameters, an input and an output, with the requisite pluses and minuses that no one understands. And then it is equal to a process which emits the output and runs in some sort of very confusing effect that no one knows. I don't know how to read this. I don't even know how to pronounce this. Is that like the country code for Iceland? It's very weird. We're gonna kind of simplify this down, right, into actually what it means under the surface, because it turns out that env is like this crazy hack that was done to like write less code, which is basically the worst reason to do a crazy hack. And yeah, all right. So this is what it actually means, really. Process 1 takes an input and an output, and it is equal to a process of read of output, and read is, oh, I guess I messed up this type signature too. Okay, use your imagination. It's basically the same thing. Read is basically a marker effect for the reader monad. The reader monad is literally just function 1, right? It takes values in from one side. So in a sense, the effect here is reading from the process that we're transforming, which is kind of cool. We're reading from one side, and that's the effect that we're performing in the transducer process. So that means that the receive 1 function is very easy to implement. It's just an await node with a read marker inside of it, and this marker effect grabs values from the other side of the stream. This whole thing is interpreted by the pipe method. And this pipe method looks for these marker effects, these readers, and it will read from the stream and give the values to the effect and perform the effect inside the transducer, and that will give us the output. So it's really, really, really cool. Really, really powerful pattern, and this is used in a couple of places in scalaz-stream and implements a lot of the combinators. But this sort of gives rise to a natural question, right? Thus, the effect that we're performing this in is the reader monad, then we can't actually run any real side effects, like talking to a server somewhere, right? Which would be a very useful thing to do, is if we could sort of get data from the left-hand side, right? And then use that to decide which server we want to talk to, and then depending on what the server tells us, we might transition to a different state in our state machine. That would be a very, very useful thing to do. And process one gives us a clean state machine encoding. It would be really nice if we could use it. The problem is that this is not quite going to work, right? If we want an effectful state machine, we need to have some way of performing effects inside of our reader monad, some sort of other branch to the reader monad that works. And this doesn't work. It turns out that we run up against some very fundamental things in the compiler that sort of prevent us from doing this. Or so I thought. And it turns out that maybe there's a really complicated and clever way, that actually not very complicated, that you can make this happen, that Miles informed me of yesterday, that I have yet to try. So maybe this will work, but to the best of my knowledge right now, it does not. If we were to do it, it would look something like this. So this is, again, very similar to the process one thing, where you'll see right in the middle we have the read case, but now rather than just having read, we also have f. And f allows us to perform some effect f of O, right? And so basically when we're moving through our transducer, when we want to perform an effect in the transducer, either we read from the left-hand side or we perform an effect like talking to a server. And then we have this function transduce that takes a process and a transducer and then returns the output process. And those of you who are really, really good at performing Scala-C type inference with your mind will see that maybe there are some problems here. And this is kind of what I was alluding to earlier. It turns out that there's an extremely well-known Scala bug that relates to this, and it's higher order unification. The type inferencer will actually not unify these two things because it's going to get stuck on like all of these type constructors that are nested inside of each other, and it's not going to work. And this is what Miles was talking about yesterday, which kind of blew my mind, and maybe will lead to a solution. We'll see. Let's hope. So all of this is quite cool. And things, and the algebra that we saw was very clever, especially the await node, right? But things are kind of going off the rails. By a very strange coincidence, that road actually looks like something that's quite close to my house. So I'm somewhat concerned that I found that. Anyway, so this is really getting quite crazy. There's a lot of complexity in how we have to use this algebra, right? The algebra is kind of cool, but like stepping, for example, right? We saw that step async example. I wasn't presenting that with any sort of naive assumption that it's easy for you or me to read. Asynchronous stepping is very hard, or concurrent stepping, and non-concurrent stepping is not really any easier. It's very complicated to step through a process, which seems like a problem, both internally and externally. These transducers that we saw, they're super, super clever, but they kind of rely on this reader monad trick thing, and it's really bulky to work with them. And then in order to implement the pipe function, we have to have this stepper. Effectful transition is maybe not possible, and this is actually a really, really, really serious problem because it means that any sinks that receive data are single state, which means that it's completely impossible to do something like multiplexing based on any sort of semantics, which seems like a serious limitation for a network library. Like, if you can't do multiplexing, what are you even doing in this business? And it turns out that it all boils down to a couple of very specific problems that we could have seen when we were designing the algebra, if we knew what we were looking for. And I'm going to call these problems false freedom. So the free monad, which as I said is the await node, is too general. Again, this is more very strangely coincidental overlap with Runar's keynote from yesterday, but free is too powerful. You can do almost anything with it, and it tells you nothing about what you're doing. Everything can be free. That doesn't mean everything should be free, but you can make it free. We want to be totalitarian programmers and not free our monads. It's just, we don't really know what we're doing. So what it boils down to is anytime we have an effect, we could have a flat map. In fact, we do have a flat map by definition. And anytime we have a flat map, we could have an effect. And so what this means is that we have to assume the existence of flat map everywhere. And when we find flat maps, we can't get rid of them because they might contain effects. So when we're sort of trying to optimize the algebra. And it also means that these flat maps, by sort of virtue of this very pessimistic assumption, sort of propagate out throughout the entire code. When we get a stream and we're trying to transform it, basically everything turns into await nodes, because await nodes are the most powerful thing in the universe, and we have to assume that we're working with await nodes because we can't get ourselves out of them once we're into them. So it's this terrible catch-22 of where everything is going to the worst common denominator, and that worst common denominator is free. So it violates what I think is an important rule of thumb, and the important rule of thumb is build the least powerful thing. It's very exciting to reach for like all this generality of like this existential type sort of hidden inside of await, and all these things are really cool and life is fun and we feel great about ourselves and go to the pub in the evening. But it's too powerful. We want to build the least powerful thing. Einstein said, do the simplest thing that could possibly work and no simpler. That's really important, especially in software. Await is basically the most powerful thing. It is the least simple thing that could work, if my double negation makes any sense there. And there's some terrible, terrible, terrible practical consequences of this. It's not just like me bemoaning the theoretical weirdness of the algebra or like the internal implementation of the concurrency. No, this is stuff that affects you, the users of scalaz-stream. One of them is the infamous, or at least infamous to me, tail flipping problem. So when you have a stream implemented in scalaz-stream and you run it through pipe, and if that stream contains an await, pipe will take the await, which was like, if you sort of think of it's like containing like this part of the stream and then there's more stream after it, it will take the end of the await and move it all the way to the end of the universe. Randomly, because it feels like it. This is a snippet of code from the actual implementation of pipe. And you don't need to like worry about understanding the majority of this. The really important stuff is like right on the line that I underlined. Because that's where we're recursively going to the next step of the process one that we were handled, next P1. And you notice just a little bit to the left of that line, we're taking cont, which is the continuation of the process that we're transforming, the continuation of the left-hand side. And we took it and we're putting it inside of the await.extend. So this is where we're taking the await node inside the process that might have stuff appended to it, and we're taking that await node and shoop all the way to the end of the universe, which may not in fact end. This is terrible because these sorts of transformations mess up a lot of assumptions that we have inside of the library, and we cannot avoid it. We can't avoid it. In fact, I have a proof that we can't avoid it because await is so general and powerful. It is impossible to implement this function without a mutable variable of some sort, and even then I don't think it would work, without doing this tail flipping thing. And it means that awful, awful things happen if you construct processes and sort of pipe them through here, which, as it turns out, is a very common thing to do. And it's happening again because the await node is everywhere, absolutely everywhere. Finalizers and preemption. Those of you who've done concurrent and asynchronous interrupts know that preemption is very hard. So that's why it's in scare quotes. These cause a lot of, these kind of relate to a lot of really confusing problems, right? And finalizers, like I said, finalizers are definitionally safe, but they interact with other features in some very strange ways. One of them is loss of associativity. So we talked about, at the beginning of the talk, we talked about the associativity of addition, which comes from group associativity and monoidal associativity. And we talked about the associativity of the monad laws and how important it is for anything that claims to be a monad to actually be a monad, to implement the associativity and obey it. Well, it turns out that process claims to be a monad, but is not actually associative. It's terrifying. It's absolutely terrifying. It's not even associative in append. It's like, what are we even doing? I don't know. It's terrible. We're fixing that in 0.8, and we're fixing it coming forward. But right now, if you use the released version of scalaz-stream, it is not associative under certain circumstances. And that blows my mind, because you try to make certain changes, or you refactor code, or you just try to write code in a way that's natural to you that you would expect to work, because associativity, and it doesn't work, or it doesn't work the way you would want. There's lost results in concurrent code paths. This is a really big one and really, really annoying. But like under certain circumstances with concurrent merges, you can actually lose errors. You can lose the specificity of your error, and your code just like silently keeps on going. That's concerning. I mean, and it comes from how some of the stepping stuff works. And our performance is terrible. I'll just come out and say it. Like, the performance of scalaz-stream is really, really, really bad. Someone did some benchmarking recently where they benchmarked it against Akka streams. Now, to put this in context, Akka streams is not optimized yet. They were focusing on getting their implementation right and sort of making things work, and then so it's very naive. And all the Akka developers sort of talked to me about it, and they were like, "Oh, don't profile Akka streams. It's terrible. It's going to be awful." And someone actually sat down and profiled it against scalaz-stream, and it beat it by like a factor of 10 or something insane. Completely unoptimized. So scalaz-stream is very, very slow, and it's slow because await is everywhere. The await node is slow. It's hard to evaluate because we have to worry about this effect, and then we have to flat map, and there might be a context shift, and we don't know what's going on, and so it's very, very, very slow. We take all this chunking, and we like shrink everything down to single element vectors, which are absurdly inefficient. Like, everything is bad. Like, life sucks. It's all bad. We're gonna start again because this is just not what's happening. So, and this is what you may have heard of as FS2, possibly FS squared. I do not actually know how to pronounce the name. We're going to call it FS squared for now until someone tells me that I'm wrong. There's a new algebra, brand new algebra, completely designed from scratch on a whiteboard, and we decided that what we needed to do was have something less powerful than free. We still need free because we still need flat map, and flat map is nice. And we don't want to constrain our effects to always be monadic because that's not very fun. But we're not going to make it so intrinsically tied to everything, right? So the free monad in the new algebra, which I'm not going to have time to show you, but the free monad in the new algebra is abstracted away from the effects. All it deals with is the structure of the stream, and then effects are their own separate thing. And so this means that when we find effects, we can't remove them because they're effects, but we don't have to worry about some other structure attached to it that we might otherwise want to manipulate. And if we find structure that we might want to manipulate, we don't have to worry about effects randomly gumming up the works when we're trying to move things around. We are trying to go about this in a relatively principled way. So we have a reference implementation and a normal form and a set of laws that this normal form has to obey, that we can check the final implementation, which will presumably be somewhat optimized, against the normal form and against the laws and make sure that we actually obey them. So no more randomly surprising everyone by losing associativity on things that you would expect to be associative. We have first class stepping. So this is something that the current library doesn't really allow us to do, right? You saw the implementation or the signature of step async. No one wants to use that. I have to use that to implement the concurrent stuff, and it sucks. No one wants to use that. The new algebra has a nice step function that's safe, that ensures that you can step processes without getting yourself into trouble or having dangling resources or impureness or anything like that. And it allows you to do it for both concurrent and non-concurrent stepping, which is really, really important. So the concurrency is sort of more first class. And just because it's fun, we actually abstracted completely away from task. So if you've ever used scalaz-stream, you'll know that almost all of your streams that do anything non-trivial just end up being task, right? Process of task of something. I have so many type aliases that are just like equal to process of task. Well, we've gone away from that. So you'll be able to use FS2 with, say, Scala futures. That would be cool. You'll be able to use it with really whatever you would want, such that you can implement a certain type class that we have defined, which defines the asynchronous behavior in a performant way. This is really, really, really cool, and I think it's a good step forward. So wrapping all of this up, this random journey through extreme coolness, what have we learned? Well, I think the number one thing we have learned is that we can generalize Victor's non-quote into software is hard. And these things are very, very difficult to get right. And even when you think you have a solution which is sort of cool and elegant and has all these nice properties, there might be something lurking in the mist that maybe you didn't expect, like, say, the free monad. So clever algebra, neat ideas, unfortunately had some problems. So we're pushing the reset button, but we learned from it, right? And I think there's always lessons to be learned from your failures. If there isn't, then they were sort of pointless. Why did you bother failing then? Constrain your generality. Don't do things that are really, really powerful just because you can, right? Ideally, do something really, really dumb and simple just because you can, right? Elegance is stupid. And stupidity is elegant. Like, that's good. Make it as simple as you can, and you can always make it more powerful later. It's hard to go in the other direction. Do not be afraid to rewrite. Now this is transitioning into like a general software methodology talk, but honestly, like don't be afraid to rewrite what you did. Scala-stream has users. It's in production. It's like managing, if you sum everybody up, it's managing tens of hundreds of millions of events per second across the world. That's like, I mean, so we're not as big as Akka, okay, then who is? But like we're not just like some random hobby project, but we're rewriting the entire system from the ground up, like internally, and we're calling it 0.9 because that's a good beginning number. But we have to rewrite it, and I think that the benefits are really, really important, and we believe very strongly that this is going to make things better. You should believe that too about your own code. You've learned something about your domain now that you've implemented it. You've learned something about the pitfalls. Take advantage of that knowledge. Do it again. Do it better. You will, I promise. Do it much better. I think we have some time, though I honestly don't know how much. Does anyone have any questions other than perhaps what the answer to this is? Because I can't tell you. Yeah. Any questions whatsoever about anything that I have said or anything that I have not said? Yes?
In your new design, do you still have the effect type parameters or covariance?
In the new design, do you have the effect type parameter covariant? That is an excellent question. And the answer is yes. Why? That is an even better question. I hate variants. It's very confusing. It causes the compiler to generate these things like any with product with serializable. And it's bad. Nobody likes it. Here is the problem. The Scala language does not have higher rank types. So what we would really want to express in process is we would want to say this process is valid for all effects, or for all effects, or for all effects of A, right? Something like that. That would be the way that we would represent a process that doesn't have any effects inside of it. The problem is that Scala does not provide us a way of writing down a type, which is for all A something or other, right? It doesn't give us that functionality. And there's various tricks that you can use to get around it under certain circumstances. If you went to John's talk yesterday, you would have seen natural transformation. That's one kind of tricky, there's a higher rank type inside of there. There's also kind of a more generalized solution inside of Scala sed, and I believe cats as well. But at the end of the day, if you want to do it in sort of a top level type, like process is, and you want your type inference to actually do sort of the right thing most of the time, you really don't have any options. So basically, as a general, abstracting to the general from this specific analog, if you're encoding an algebra or an algebraic data type, and that algebraic data type needs to have a universal inside of it, a higher rank universal inside of it, as process does, you actually need to encode it with covariance. Otherwise, it won't infer properly.
So it's only so you can put nothing in there.
It's only so we can put nothing in there.
Create a nothing.
So you can't create a nothing.
Well, you can create a new type called literally nothing, but which has the same signature, or how do you say that?
Yes, so we could create a new type that is not literally nothing but has the same signature. Actually, you can't. You can't do it in such a way that it fits in the type system. That's the problem of not having higher ranked types. Nothing is not a type that we can derive as a type. I mean, certainly not values of it, but we can't actually roll our own nothing in Scala because we don't have higher ranked types. What we would want to write, yes, Miles? Yes?
So you can do some really weird things. I discovered this quite recently. I think it's what the guy asking the question was referring to. You can actually add a refinement to nothing, and it will behave like nothing, except that it won't be treated as unsolved by the type inference algorithm.
You're a horrible human being. So for the video, what Miles is saying, and I'm not even sure I want to preserve this for posterity, but you can add a type refinement to nothing. I can't preserve this for posterity. You write it down somewhere. This is terrible.
It's preserved for posterity. It's on a ticket on the Scala-C issue tracker.
Okay, it's an issue on Scala-C, which is good because those get resolved really quickly. So we won't have this for very long. You're a horrible human being. Oh my gosh. So maybe there is a better solution then. Yes.
So will your final algebra maybe be a nested one or something, where on the one hand you have the kind of monadic one for more dealing with the sequential thing, and then embedded you will have an algebra that is more doing the effects in a sequential or concurrent way?
Yes.
Okay.
So the question was, is the final algebra going to be some sort of nested thing where you have your one algebra for doing the free monad and the structure and the other algebra for doing the effects? Yes! Yes! That's exactly what it is. And I think that's actually fundamental. It turns out to be in the opposite order. So the effect stuff and the appends and things, which are sort of like an effect, is at one level. And then there's a free algebra kind of that you can branch out inside of that. And you're unambiguously in one algebra or another at any given point in time. I'm going to loop back to you and then come down here. Someone?
I'm just saying that you said that don't be afraid to rewrite, but also that you've got lots of users. So how source compatible for your users is the rewrite going to be?
That is a good question. So the question is, how source compatible for the users is the rewrite going to be? Because screwing your users is never a good idea. The answer is basically as source compatible as we can. Anything that's sort of surface level that you're doing with scalaz-stream will basically work with FS2 basically without modification other than your imports. Anything, if you're using process one, like you have custom process ones, those will have to change because those are completely different in the new FS2. They support effects, yay! But they are very different, so you'll have to modify that. But for the most part, we're trying to keep kind of the mainstream stuff working because that is important. I'm gonna yes.
Hi there. You were speaking about laws earlier, and I was wondering if you actually managed to express these laws and test them with discipline or something like that.
Yes. So I was talking about laws, and the question was whether or not we could test them and express them, and the answer is yes. So there's some nice tooling that's been built up around ScalaCheck for doing this, obviously in ScalaSed and now in CATS. We're not using that tooling just yet, but I think we should be. We're sort of ad hocing it. But yes, if you look on the FS2 branch, there are laws and there are laws that are tested. Those laws are not expressed in any concise individual place in sort of mathematical freehand notation, which is what I would like. One of my many stack of projects that I need to get to is that one right there. But yes, the laws are tested, and I think that especially with the normal form, if we ever get to a point where we've sort of accidentally moved away from that, the test should catch it, unless it's really arcane. Mike?
Yeah, there were a few spots in the redesign where nothing was being retracted. And if it hasn't hit the branch yet, I think Paul's looking at using Miles's refine nothing to work around that very issue. So it might even be in the branch today. You're not responsible.
The code is on my hard drive in a Git repo. This is sort of polluting my computer. Oh my gosh. So for the video, Mike was saying that Miles's nothing trick, which horrifies me, might actually already be there before I was able to object. Wow, that's terrible. That's so terrible. I think, did you have another question?
No, I didn't have another question. I just raised my thumb just like you did.
Oh, okay. Awesome. Anybody else have any questions? No? All right. Have a good day. Build awesome stuff.